Altitudes and medians. We're going to look at the last two sets of lines that you can use within triangles that do create points of concurrency. The first is going to be the altitude. An altitude is a perpendicular segment from one vertex to the opposite side. For example, in this first picture here, the altitude would be the segment here, assuming that that would be a perpendicular. That would be the altitude. Altitudes can be inside, outside, or on the triangle. It really just depends on the type of triangle that you do have and the way that you have that triangle positioned. Okay, every triangle is going to have 3 different altitudes because you actually have 3 different sides that you can connect to opposite vertices. For example, this picture is actually the same triangle, just rotated to the side. Okay, so for this one, yes, it does have an altitude here, which would be identical to the one shown there, but you can also do this. You could imagine the base extended out. Let's make that look just a little bit better there. All right, you can imagine the base extended out, and then you could draw the altitude outside of the triangle. You could show it here. Okay, so you'd have that base, there's a little bit of a space here, and then you've got the altitude shown there. So you just imagine that segment going outside. In addition to that, you could have an altitude that would extend off of this side here. You'd also have to extend outward, and then the altitude would be located here. So it is interesting that the altitudes would have a point of concurrency. The reason is because those altitudes could exist on the outside of the triangle. All right, so for simplicity, what I'm going to do is start with a picture that would have the point of concurrency inside the triangle. Once I finish that up, I'll show you a picture of an example where it is on the outside. All right, so to make sure that the point of concurrency is inside, what I would need to do is work with an acute triangle. I'd have to have an acute triangle. If it's obtuse, that will put it on the outside. All right, let's go ahead and label some things here just in case. We got A, we got B, we got C. Okay, to make an altitude, right, I need an altitude here. Okay, and I can sort of eyeball it. I don't think that would be like too terrible of an idea because you do have these little lines on the ruler that you could use to make sure that it's pretty close to being perpendicular. However, you can also do this. You can fold the base onto itself just before you make a crease. Make sure that you got the vertice sitting on that crease. Okay, so if I do that, that will give me a perpendicular for sure. When I fold it over, that's how I get that perpendicular. All right, and then making sure the crease goes to the point, that is going to give me an altitude. All right, for the other sides, B, go ahead and fold that over onto itself towards C. It does not fold all the way to the other end, right? We're just going to fold it over up until we get the vertice sitting on that crease. So we open that up. Right, there's our second altitude. Okay, so of course, these two are going to meet, and there's no real big deal about that. But when we do the third one, we're going to notice that they all make contact. All right, so my attention is going to be on making sure that that's overlapping correctly, and then moving it along until it appears that the crease right there. So this one is almost isosceles, if you can see through that part there. It is pretty darn close to isosceles. But most importantly here, when I draw it, when I fold it, and then when I draw it, you see that these are all going to meet at one single spot located right here. And that is going to be called the orthocenter. Unfortunately, the orthocenter doesn't do anything special. You can't use it to make any circles, do anything interesting like that. And more or less, it's just kind of interesting that all these altitudes actually meet in the same spot. The prefix ortho refers to being straight. Altitudes are considered a straight segment with respect to the base that they meet because we have those set at a perpendicular. All right, just for the sake of demonstration here, what I am going to do is show you that the altitudes can meet up outside of the triangle. which on its own is a little bit of a weird thing because an altitude is a measurement that is inside of the triangle, and that's usually all we care about. For example, the base here, the base of that triangle, the altitude, see if we can fold this, get that vertice there. All right, the altitude would be just the piece right here. That would be it. That would be the altitude as far as how we'd be concerned with it for like actual calculations, like maybe the area of a triangle. Okay, that would be the altitude. However, notice the crease that it follows along that direction. Go ahead and make that a little bit better as a crease. All right, so the other ones, this is where it gets a bit confusing. This base right here, we're gonna have to extend it out so that we can make a perpendicular up to that point. Okay, so try and maybe do those just as dashed lines. See if this will work. All right, and then I'm gonna fold it onto itself until that point is up at the top. Okay, this is gonna be my best shot at getting perpendiculars, because if I don't actually have perpendiculars, you know, they're not gonna meet up. It's not gonna work. Okay, so that would be an altitude. That altitude is located on the outside, but if you still need to do like a calculation for area, what you would take is 1/2 base times height. That would be 1/2 of this length multiplied by that length, okay? Where is the third one? Over here. All right, so here's our third one. We're gonna let that be the base. That means that I need to extend it out. Okay, I'm gonna fold that onto itself. Might have to do this one backwards. Okay, so folding over until I get that vertice right up there. It might be a little bit crooked. All right. Go ahead and highlight. This is the altitude that we'd be concerned with as far as measurement size. But, here, we'll turn it this way. But if you look at all of the creases, right? If you look at all the creases, I'll go ahead and follow those out a little bit. See if I can make it a little bit lighter. There's that altitude. There was this one. And last, there's that one. Okay, so the picture now looks like a big mess. Remember, this is the original triangle, right? That would be the original triangle that we have. This point is the orthocenter. Okay, so it can exist on the outside. All right, so the orthocenter really didn't provide anything special with it. It was interesting that all the altitudes meet at the orthocenter. However, there isn't any calculation, there isn't any sort of circle that you can make or anything that is like really interesting beyond the point that they all meet at that single location. However, the median, which is gonna be our fourth one here, this is a really important one here. There's one type of a calculation that you're gonna be able to use in this class, but then there's another thing about the median which is really neat and applies to engineering. All right, so future engineers, you're gonna hear about the median again, okay? And at the end of the video, I'll talk about why you're gonna hear about that. All right, so first off, a median is a segment that connects a vertex to the midpoint of the opposite side. Okay, let's go ahead and draw a picture of a triangle. All right, the type of a triangle that we have, it doesn't really matter that we have here. It's not a big deal if it's obtuse or acute or right. Okay, it'll all work out fine. Okay, we'll go ahead and call this ABC again. All right, so a median is gonna connect a vertex to the opposite side, but it is not gonna make contact necessarily at a perpendicular. That would be the altitude. Instead, what we're gonna need to do is find the midpoint and connect that point to the opposite vertex. All right, so to do that, you're gonna treat it sort of like a perpendicular bisector, except we don't need a crease, okay? Just a little pinch right there. Fold it over C to A, make a pinch. We don't need a crease, just a pinch. That way we can get a midpoint and then we can connect that to B. So we did not want the crease, okay? All right, so for the others, let's see here. From A, what we'll do is match up B and C. Put a little pinch right there. There's your points. We'll do some double markings because these will be different. Go ahead and connect that to A. Okay, we got another median there. Last, get the midpoint here. little pinch, not a crease, triple mark, because these are going to be different. All right, and look at that. Before I even draw it, I'm matching up this, I'm matching up to the midpoint. It's going to make contact at the exact same point. And that's, all right, so that would be the connection of all the medians. That one has a very special name. Special because you're going to use this a lot in the future, especially future engineers. It is called the, ooh, I misspelled it there. All right, I may have been watching too many Star Wars movies. This is not a Centroid. Centroid. That is a Centroid. That was close-ish, I guess. It's called a Centroid. All right, so the Centroid, the place that where all the medians meet up, does have a mathematical property that we need to look at for geometry. It's going to be a bit tough to determine it exactly here, so it's really dependent on how well I did the picture, but we're going to be looking to complete this statement. The centroid of a triangle will divide each median into a blank to blank ratio. Okay, the way that the centroid splits each of the medians is going to be consistent between all of them. Okay, if we just look at A to that point, that does not cut it in half, right? That point is definitely not in the middle. It should be more around here. Okay, so I'm going to try this with just taking measurements first and see if I get lucky on how these look. Okay, it's going to work out pretty good for the first one here. All right, we get a measurement from A to the centroid, 4 centimeters, and then the other half is going to be 4 to 6, so that's 2 centimeters. Okay, so in a comparison, we get 4 to 2. You get 4 to 2. All right, the other ones would probably not be as quite what we want here. Well, that one might work. I'll adjust the numbers just slightly because I think they're partial. Okay, right here it looks like I've got, we'll call it 3.6. We'll call that 3.6. I have it over here. 3.6 to the other part is gonna look like, we're getting pretty close to 2. We're gonna say, because I know what I need here, it's gonna be 1.8. Okay, now the other one might not turn out as great, so I'm just gonna stick to these 2 examples. The first was awesome, right? 2 to 4, I think we can see the comparison. And then when you look at these 2, that comparison will hold true, which is that you could take the short part, multiply it by 2, you get the longer part. The longer part is going to be twice the length of the shorter one. So the centroid of a triangle will divide each median into a 1 to 2 ratio. One part will be twice the length of the other. For example 1, we are given a picture here of a triangle. It does have a lot of points that are labeled, and we can probably figure out that what we're going to be told is that these are each going to be medians. All right, so let's go ahead and see what it does tell us. There are 3 paths through a triangular park. Okay, so there they are right there. There's the paths. Each path goes from the midpoint, okay, so the midpoint of one edge to the opposite corner. That would mean that these are medians. All right, so if SC is 2,100 feet, SC right there, that's 2,100. Not sure if I can label that in picture, so I'll make a mental note that this is 2,100 feet. BA is a side length here. That's going to be 2,500 feet. Now I can use that already because this is a midpoint, so I can split that, call them each 1,250. I could do that. All right, PR right here, 650 feet. All right, so we got that. What we're asked to do here is to find the perimeter of triangle BSP. So where is that at? Here's B, here's S, there's P. Oh, so it's just a little triangle that we have there. I'll go ahead and highlight it. All right, so in other words, we need to know all the segments. One of them we've got, the 1,250, we already got that one. All right, for the other 2, let's see here. PR is 650, okay, 650. So if we have a 1 to 2 ratio, if we do have that, we can just double that number. That will give us 1,300. That'd be 1,300, so now we've got that. It's 1,250 plus 1,300 plus whatever that turns out to be here. What is that? I got to go back to this. SC is 2,100 feet. The whole length is 2,100 feet. That does need to get split into a 2-to-1 ratio. So if I divide it by 3, divide that by 3, I get 700. So that means we're going to have 700 and 1,400. All right, and the piece we want is the short one, which will be the 700. So if we add all that up together, that will make 2,000. So we're going to get 3,250 feet. There we are. All right, and last what I want to do is a demonstration for the future engineers. Here is a picture of a triangle with all the medians drawn. To do that, I actually folded corner to corner, made little pinches, and then drew the line. That way I could get this as perfect as possible. Okay, and this is on a cardstock piece of paper, so it's a little bit harder. It's going to hold its shape. One thing about the medians is that the median, in a sense, divides the triangle in half by its mass. It divides it in half by its mass. So if I were to take it and put it on top of a pencil like that, if I get it just right, and it might be hard to tell in the video there, but if I line up a median with a pencil, it actually balances. Any bit to the left or right, you might even see it moving just a little bit as I'm talking it. It's moving it a little bit. But if I bump it just a tad bit, it will fall. It will make contact with the side. So if you get the exact spot, if you can get that median exactly right, that one's a little bit harder there. If you can get it exactly right, you can see that it can balance in that spot, and I'll tap it so you know that it was actually balanced. There it is, and then it falls off. But even better than that, which I don't think that I can demonstrate here because of the way I'm recording it, the centroid, the point where all these meet, okay, it's not just that the median will balance the weight to the left and the right of that line, but the centroid is going to balance the mass completely around it, which means that you should be able to take that and balance it on the end. You should be able to balance it on the end of a pencil or a pen. You might want to not go like too much of a pointed item, and I'm just trying to guess where the median, or sorry, the centroid, just trying to guess where the centroid is, because I can't see it here. And I got it. That will be the one in single spot where you can keep that balanced on the tip, and I'll knock it over just so you can see that this actually was balancing. There it was. All right, so a median will balance the mass left and right, but a centroid will balance the mass completely around that so you can identify a center of mass, which is going to be important for all of you future engineers. Okay, so I actually had one more thing to share with you. In a set of numbers, the median is the measure of central tendency, referring to the middle number, which is splitting the data in half. So we have measures of central tendency, which would be the mean, the median, and the mode. The median is the measure of central tendency that would have you list all the values in order, and then you grab the middle number. Okay, similarly, the median of a triangle divides the triangle in half. It separates the mass in half, and that's how we're able to balance the triangle.
Later, blah.